Hello, folks. This is Jim with Science Talk. Um, Trying something new here. You might notice that there's no backdrop behind me. I've gotten some comments about folks finding that distracting, and so I'm doing away with it. I thought seeing the clutter behind me would be distracting as opposed to a neutral sheet, but whatever. I did move some of the clutter behind me, so hopefully it's not too horrible. Um, Doing something new here in addition, trying some new software. So what I want to discuss with you is statistics. You've heard me mention a lot of my previous videos when talking about regression models and an R-square, which is how good the data fits the model line or the regression line, and how much of the variation one or more variables can explain of the data set that's seen. So, and I don't want to turn this into a stat course here. I just want to kind of give you the bare bones. Let's start with this basic situation. Let's say you have two candidates running for some public office. And a poll will show candidate X has 47% of the population, candidate Y 44%, plus or minus 4 points. Well, what does that mean? Well, let's take candidate X, plus or minus 4. So the range of the percent of people that would vote for this guy or gal might be anywhere from 43 to 51. Likewise, for candidate Y, it might be anywhere from 40 to 48. So as you can see, if you look at the low end to the high end, the low end of candidate X to the high end of candidate Y, there's a 5-point range where they overlap, 43 to 48. Translation is that this is a statistical tie. It's a dead heat. So the media may be reporting, oh, this candidate has a 3-point lead and is on the way to winning. Not so fast. So what I'm hoping is that at the end of this video that you have a kind of a more critical eye to looking at how stats are reported. Now, if you have a background in stats, if you use stats a lot in your work, you can probably skip this video. I'm not going to say anything earth-shattering new. So, but let's start with what's going on here with the, let's see, I want to go to, here we go. This here is the normal distribution. And you see, it looks like here, a couple of features about it. The two tails, as we call them, stretch out to infinity, negative and positive. So it never touches the horizontal axis. So it's called a horizontal asymptote. But the area under the curve, so you do a little basic integration, the area under the curve equals 1. You also notice that you see what? You see a peak right here at 0. Now I'll explain what the 0 means in a moment. You'll see they place a random and arbitrarily place Z value here. This is a location, a Z score. These are the Z scores here. And the shaded stuff to the left gives you the area to the left of whatever that Z score might be. If I want to know the area to the right of that location, I simply subtract whatever this area is from 1. Now, if you look in this table here, you see all these numbers taken out the 4 decimal places? These are all areas. So if I have a Z-score of, let's say, minus 2.91, right? Minus 2.9, and that's the second decimal, 1, 0.0018. That means the area to the left of that value, minus 2.91, is 0018. The areas are also correspond to the probability. So the probability of getting a value less than minus 2.91 is 0018. That's the probability. I can go on the flip side of that. Let's say I want to look at positive 2.91. That will be here. And you'll see I have what? Right here, 9982. Okay, 2.91. Well, if I subtracted the 0018 from 1, I get what? 9982. So what this tells us is, as is indicated by the curve here, that the distribution is symmetrical. And now I see how this is all shaded this way. So the z-score gives the area or probability to the left of. If you want to know the probability to the right, you subtract from 1. So what is the z-score? The z-score is a way to standardize your values, whatever your observations are. You have a set of observation, you want to calculate a mean and a standard deviation. The z-score will then allow you to take whatever your observation is and calculate a standardized z-score. Now, it's a very easy formula. Let's pull a pen up and let's do blue. So let's say z is equal to x. X will be whatever my individual observation is. I'll even give it a x sub I minus, this is the Greek letter mu, divided through by sigma. Now, mu is the mean for the population, the average. Sigma is the standard deviation. That is a measure of spread. I could have two populations with the exact same sigma, exact same mean, but they'll have two different standard deviations. The one that has the largest standard deviation indicates a wider spread to the data. So, mu and sigma are parameters. Okay. This is used when we know the population, when we have every single measurement from a population. For example, I have a class of 200 students, I give a test. I want to know what is the mean and standard deviation of the test results of that class. My population is that class. Okay. I can then calculate mu and sigma. These are called parameters. But if I want to go out in the woods and I want to measure the DBH, diameter breast height of, say, birch trees, am I going to be able to measure every single tree out there? No. Not feasible, not practical, not likely. Just logistics alone, it's not going to happen. So what happens is we do what? We take a sample. So now my sample, instead of calculating mu, I calculate x bar. Instead of calculating sigma, I calculate s. Okay. X bar and s are statistics that estimate, respectively, mu, the mean, and sigma, the standard deviation. And you'll see this reported like this in papers. They took a bunch of measurements, and you'll see they'll have a table, they'll list with the values, whatever, then you might see something like x bar plus or minus s. The mean plus or minus the standard deviation. So now, let's go back to this curve here. What's this 0? Well, let's say I have an observation, and my observation equals the population mean. Then guess what? I'm going to have that same value here and here in the numerator. That gives me 0. So a z-score equaling to 0 is a value found right at the mean. Typically, the z-scores have a range of -3 to +3. In fact, this will typically contain over 99% of the data. Okay. Will contain over 99% of the data, about 99.97 or so. And if we look at here, if you look at the shape of the normal distribution here, right about where what's called the inflection point, where the concavity of the curve changes, is about where we see the z-score of -1 here and +1 here. If we were to drop vertical lines and determine the area under that curve there, we will find that basically it's from here to 0 will be 0.34, then 0.34 from 0 to +1, -1 to 0, 0 to 1, basically adds up to 0.68. In other words, 68% of the distribution of your observation will fall in the range of z equals -1 to z equals +1. What is the significance of -1 and +1? When z equals -1, that is one standard deviation below the mean. Likewise, +1 is one standard deviation above the mean. And you can do likewise for -2, +2, -3, +3. 2 standard deviations below, 2 standard deviations above, etc. And when you go from 2 standard deviations below to 2 standard deviations above, that accounts for 95.44% of your distribution. That leads us, and from -3 to 3 is that 99.97 I just mentioned. So we have the 68, 95.44, 99.97 rule. For ±1, ±2, ±3 standard deviations, or ±1, 2, 3 for the z-scores. Okay. That gives you a quick, you can tell quickly how your data is spread about, how it's distributed. And we can determine percentiles and so on and so forth. Basically, if you have a z-score of -1, that basically, this is half, so that's going to be 0.5. 0.5 minus 0.34 is 0.16. So if you have a z-score of -1, you are in the 16th percentile. So how does this help us with, when you look at probability and significance? Well, there's always going to be randomness in a system. Right? People have different heights, different weights, and so forth. It's randomness. When we're doing statistical testing, we are basically looking at what is the probability that the differences we are seeing are due to just basic randomness in the system, or cannot be explained completely by randomness in the system and is something else at work. So when we do hypothesis testing, we're basically having a null hypothesis, H sub 0, which, and I'm just basically going to say, in essence, that any differences we see is strictly due to the general randomness in the system. And if that's the case, when we accept HO, the null hypothesis, it's typically giving us an insignificant result. Conversely, we have the alternate hypothesis, which in general terms basically saying the differences that we are observing is not due to simple randomness of the system. And we thus have a significant result, meaning the differences are significant because it is not simply randomness, but something else happening, some factor, if you will. This is where statistical testing comes in. Now, in the video I just did, where I talked about the association between disruption of the biorhythms and mental disorders, I said what? There was an association, but no causality. Causality is determined when you collect measurements, you collect data, and you analyze it. You analyze it statistically, and you are doing hypothesis testing. So whatever the method that you're using, you calculate what we call a test value, and you compare that test value to the critical value. And typically, usually, if you want to think in terms of the absolute value, if the test value is greater than the critical value, we have a significant result. Let me give you an example. And I'm going to just briefly scroll down to the t-tables here. T-tables, here we go. T-tables here. Now the t-tables is not the exact same thing as the normal distribution. You'll notice that the area given is to the right, not to the left as in the z-score. But as you increase what we call the degrees of freedom, basically the allowable data that you can work with, as this gets higher and higher, the shape of the t-curve becomes more and more closer to the normal distribution. In fact, you scroll all the way down here, 1.645 is a critical value for testing at the 95% level using the normal distribution. And if you look at the t, it differs only in the third decimal place, the thousand. We have 1.646. Likewise, if you're now the Z025, this is when you take the 95% level and do a two-tailed test. I'll explain that momentarily. But the critical value is 1.96. Again, very close. If we're at the 99% level, the critical value at the Z is 2.326, 2.328. Again, very close. And this is the 95% level taken at the doing a two-tailed test. And again, you can see that's very closely. Very quickly, a one-tailed test, something like we see here and here. We're simply looking at, let me go back to here. We're looking at, is HO or less than or equal to HA? It might be a threshold level. So are we testing less than? That'll be a left-hand test. Or is it greater than? That'll be a right-hand test. And that would be a one-tailed test. We're looking for directionality, if you will. A two-tailed test is simply, does it not equal? So it could be less than or greater than. We just want to know HO. The differences, there is no difference, they're equal. HA, there is a difference, they're not equal. We're not concerned if it's greater than or less than. It's just simply, are they equal or not? So this one, we're just interested in not being equal. That's a two-tailed test. And a two-tailed test means that, going back to the Z distribution, T, going back to the Z distribution, we're looking at this end and that end as well. So let's say I calculate, I just want to briefly give you an example of a Z calculation. Let's say I calculate a Z-score, substituting into that formula, and let's say it's 2.22. Okay, here's 2.2, that's 0, 1, 2. So this is the probability. Now, that's 0.9868. And remember, for Z distribution, it gives it to the left. So that means the probability of having a score of 2.22 less than that is 0.9868. The probability of having a Z-score greater than 2.22, you would take this and subtract it from 1, because the area under the curve equals 1. So, back to this. There are a couple of ways to determine whether we have a significant result or not. We can calculate what we call a test value, a test statistic, and we compare it to a critical value. So the critical values, these are typical critical values if you're using Z or the T distribution, 1.645, okay? And that would be at the 95% level, 2.326 if you're at the 99% level. What is meant by the 95 and 99% level? Basically, when we say something is significant at the 95% level, we're basically saying that the differences we're seeing happens in basically 5% of the cases, 100 minus 95. That means since it only occurs in 5 times out of 100, the difference is more than likely not due to simple randomness. Likewise, 99% level, the differences we're seeing really happens just 1% at a time, and it's not due to randomness, so there is something happening. So let's say I work with this value here, 2.326. Okay. So 2.326. I run my test. This is at the 99% level. I run my test. Let's say I get a test value, and it is 2.91. That is greater than the critical value. This is the critical value. That is greater. We thus have a significant result. We would reject HO and accept HA. Likewise, if my test value was 1.84, that is less than 2.326, we have an insignificant result. The differences we are seeing is simply due to randomness. Nothing extraordinary happening here. Now, let's look these up here. 2.91. We already know, and I'm going to write down here, my critical p-value is 0.01, since we're at the 99% level, subtracted from 100. So, let me see, what was that value? 2.91. Okay. Let's go and look at the z table for 2.91. 2.91, okay, that's 0.9982. But this gives the area to the left. We want to subtract that from 1, and I'll just play a little trick here and go with minus 2.91, because it's a symmetrical curve. And we see what? 0, 0, 18. Okay, so let me write that down. 0, 0, 18. And we'll put a decimal there. Let's do likewise for 1.84. And I'll kind of cheat a little bit and go with minus 1.84. And we have 0.329. Okay, 0.329. Okay, let's put a little line there separating that. So now, you see here how the test value is greater than the critical value. And what we see here with the corresponding p-values, it's less than. So in other words, typically, if your test value is greater than the critical value, along with the probability value, the calculated p-value being less than the critical value, you have a significant result. They support each other here. And you'll notice that this is less than, and this is greater than. So if your test value is less than the critical, insignificant, and correspondingly to that, the p-value will be greater than the critical p-value. Now, I chose this example because I want to illustrate something here. We know that if I was at the 95% level, this is my critical value. Hello, come on. It's supposed to be 5 there. Okay, 0.01. 0.05. Now, this first situation here, if it was significant at the 99% level, it will be significant at the 95% level, because the probability is getting smaller and smaller. You're getting to more and more restricted area. But what if in this test here, what if the level of significance was 95%? Well, now look at this here. 0.3 is less than 0.5. 1.84 is greater than 1.645. So based on the numbers, we would have significance at the 95% level. This is a weak significance. So one thing I always look at, no matter what the test is done, if it's ANOVA, if it's chi-square, if it's testing coefficient, t-test, no matter what it is, I look at the calculated p-value. If I see something like this, I'm going to be questioning really if the studies has really demonstrated what they set out to demonstrate. But this is a weak significance. This is something you can like now look for when you look at papers. Now, oftentimes I'll see something like this in the paper. You know, they'll present the result and they say p less than 0. And they just rattle off a whole bunch of zeros. Something like that. Okay, yeah, there's no question about that. This is a significant result. You know, it's less than 1/10,000. Okay, I mean, we're really out there. So, this is how you know if you have a significance. Is the test value greater than the critical value, or is the test p-value less than the critical p-value? And if so, by how much? So with that in mind, you can now start, you can look at these papers and say, aha, he's got a point. He's saying, oh, I'm significant at 95% level, but he's got a 0.3 probability. Because 0.3, yeah, maybe significance at the 95, but it's not significant at the 99. It's in between. That's what I mean by it's weakly significant. The trend lately, and I think justifiably, is to work with the 99% level. Because if you have significance there, then there's no doubt to the result. Sometimes you will see in papers saying, we tested a 99% level, it was not significant. It was significant at the 95% level, but it's obviously weakly significant. You will see that written up in the papers. And correctly so. So just wanted to give you a couple, I guess you could say, arrows for your quiver there. Is that what it is? Yeah, that's the quiver back there. So that you can have a little more critical eye when you're looking at, when stats are reported. So anyway, I think I'll stop that here. I don't want to get too far into this or totally bore you guys, but I thought I would do something like this and see, and I hope this helps. So, and we can do, for example, when we do regression analysis, there is a specific test to test the slope of the line to make sure it does not equal 0. Or the null hypothesis is that the slope of the line equals 0. If the slope of the line is 0, we have a horizontal flat line that's a constant function. There's nothing happening other than being a constant function. But there's no relationship between the independent variable and the dependent variable. But if we get a significant result, we reject the null hypothesis in favor of the alternate hypothesis and say the slope does not equal 0. Oh, now the variables are related. Then that leads us to an R square value and an R value and so on. And oftentimes, if the slope is equal to 0 statistically, the R square will be poor, will be a low value. So if you guys want, I could do another video on regression models, the simple one. Let me know. So anyway, let me stop that here. I hope you found this informative, because stats, math is a huge part of science these days. Just can't escape it. So thank you for your time, and we'll talk soon. Hey folks, just a reminder to please subscribe and click the bell so you know when I drop a video. And please share my work with others. Please tell them of my channel. And I hope you'll become a patron at Patreon. I place videos on there from time to time exclusively for my patrons there. If you're already a patron, thank you for your support and continued support. Details in the box below. Thanks.